Good morning. Today we are going to discuss what is a counter. Counter is one of the very important sequential circuits. For example, suppose that in a counter you can count like 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. After that again you can count 0, 1, 2, 3, etc. up to 9, 0, 1, 2, 3, etc. up to 9, etc. etc. That means counter means after some state it is switching to some other state, and after that switching to some other state and something like that. For example, suppose that you have a counter like initially you have 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1, and suppose that it is coming back to 0, 0, 0. Again you are doing like this. This is a kind of a counter. Suppose that another counter you are going to have, initially you have 0, 0, 0, and afterwards suppose that if you want to have 1, 0, 0, after that you can have 0, 1, 0, after that 1, 1, 1, again you are going back. That means you can have a counter, and according to the requirement you can design your own counters. Okay, you can have different types of counters, and it's an application. On application of clock pulses, it goes through a sequence of states. That means after applying each clock pulse, that means if you are giving an excitation to a flip flop using a clock pulse, they either stays in the same state or it is switching to some other state. Okay, that depends. So this is an example of a counter, and counter is we can have a life cycle stages of a counter. That means after initially you have a condition. Suppose that you have here for this 0, 0, 0, 0, 0, 1, 0, 1, 0, etc. For storing each bit you need a flip flop. That means this is flip flop number 1, flip flop number 2, and flip flop number 3. Here you have 3 flip flops, and suppose that this is the most significant bit and this is the least significant bit. Okay, and this is, and suppose that here the output of this is say this is 1, 2, 3, this is Q3, Q2, Q1, this is Q3, this is Q2, and this is Q1, and you have a you have clocks, and according to that when you are designing a counter you should be aware of what is a counter. And initially here we have a number of types of counters, asynchronous as well as synchronous counters. Asynchronous counter means for storing each bit of information you need a flip flop, and suppose that you have 3 flip flops. Here we have 3 flip flops, and for storing Q3, Q2, and Q1, for storing this Q3 the most significant bit you need a flip flop, and for storing this bit you need another flip flop, and for storing this bit you need another flip flop. Okay, and now suppose that all the flip flops are triggered using a common clock. All of them are triggered using a common clock we call as a synchronous counter. That means all of them are activating or it is triggering at the same time, the zeroing at the same time. But in an asynchronous counter, initially here we are going to have a clock pulse. Here clock is applied here, and for this Q2 we are going to have, that means output of the first flip flop is given as the clock pulse of the second input, second flip flop, and the output of that is fed to the third flip flop as its clock. That means here all these flip flops are not triggered using a single clock. Here an external clock is given to this flip flop. The output of this is fed as the clock pulse of this, and the output of this flip flop is given as the clock pulse of this. And this is an example of an asynchronous counter. In a synchronous counter, all the flip-flops are triggered using a common clock. See, this is called ripple counter. Ripple counter, that means in this asynchronous counters have a number of limitations, and that we will discuss when we are discussing when we will discuss that in detail. Output of one flip flop is given as the clock input of the next flip flop. Flip flops are not clocked using a common clock. Circuit is simple. The design is very simple. That means no more circuitry has to be provided here. Here this is simple. That means output of one is given as the clock input of the other, and the output of that is second flip flop is given as the clock input of the third one. And the design is very simple, but it can be used only for ripple counters. That means this is an example of a ripple counter. It is changing from 0 to 1, 1 to 0, 0 to 1, 1 to 0, 0 to 1, etc. That means here whenever there is a change from 1 to 0, this is set. Here there is 1 to 0, then it is reset. Here 1 to 0 change, it is set, and here if you have a transition from 1 to 0, again this will be reset, and that we'll discuss later. Anyway, ripple counters are examples for asynchronous counters. In a synchronous counter, clock is given simultaneously to all the, see, suppose that here, and this is the common clock. Now we are applying this common clock to all this, and now this is a synchronous counter. Flip-flops are clocked simultaneously. That is why the name synchronous counter. When number of states increases, the circuit will become complicated. That means, suppose that if you have a number of states, for example, here this is a 3-bit counter. Suppose that you have 4-bit, 5-bit, 6-bit, etc. Then if the number of states or number of flip-flops increases, then the circuits will become complicated. And as it is triggered using a common clock, then this is a fast circuitry. This is a very fast counter compared to this. This is slow, means this ripple has to go from here to here. That means from the first flip flop, some ripple has to initiate, and that ripple has to carry out to the last phase. That means it is taking time, and the propagation delay is a bottleneck, and in that case speed is low as clock propagates through the different states. And that's all about counters, an introduction to counters. And now in the next section we are going to discuss asynchronous counters in detail.